last week we talked about Euler circuits. And an Euler circuit was a circuit that hit each edge exactly once. And in doing that, you could hit the same vertex multiple times, but you had to hit each edge exactly once. There's a similar notion called a Hamiltonian circuit. A circuit, definition, a circuit that visits each vertex once and only once is called a Hamiltonian circuit. So a Hamiltonian circuit is going to be a circuit, so it has to start and end at the same vertex. It hits each vertex once and only once. I mean, except the beginning and ending one. You start and end at it. But all the other vertices, you hit once and only once. We call that a Hamiltonian circuit. So this remark just differentiates between Euler and Hamiltonian circuits. Euler circuits hit each edge exactly once, and Hamiltonian circuits hit each vertex exactly once. And the way I like to differentiate between them is Euler and edge both start with E. That's really the only way I differentiate between them. Hamiltonian circuits hit each vertex once and only once. So some applications of Euler circuits were when we were looking at parking meters, when we were looking at delivering mail, hitting mailboxes. Now, what types of situations could you want to find a Hamiltonian circuit where you want to hit a bunch of different, say, stations? Well, you could be a bus driver and you're looking to hit a bunch of different bus stops. So you'd want to find, in this graph here, if you wanted to if you started somewhere, you wanted to hit every bus stop and then you wanted to go back home, well, you would start at, say, A, try to hit every bus stop, and then get back to A. You could also be checking those large mailboxes where they, you see large mailboxes sometimes on the side of the street where they store some mail for the mailman to pick up. You could be delivering mail to all of those mail stations. Well, in that case, you'd also want to hit a bunch of different certain spots. And there are many other types of things. And one example in the book I liked was if you're a lobster fisherman and you're looking at a bunch of your different lobster cages, like stations where you have lobster cages. Well, that'd be the same type of thing. You want to start and end at home, and then you want to hit all of your different places where you catch lobsters. So let's, before doing any applications like that, let's just look at this graph and find some Hamiltonian circuits. Now, before doing that, whether a graph had an Euler circuit, two relatively simple conditions were all we needed. We needed a connected graph, and we needed the valences to all be even. Whether a graph has a Hamiltonian circuit is, in general, a much more difficult problem. It's actually a very difficult problem in math, whether a given graph has a Hamiltonian circuit. So if in this class you're given one that says find a Hamiltonian circuit, well, there will be at least one that exists. So here, let's just look at this example. Find two Hamiltonian circuits in the graph. Well, I'll give you a head start. Okay, so hopefully you're ahead of me. I'm going to start at A, then I'm going to go over to B, and just to keep track of the ones I hit, I'm just going to fill in these dots a little more. So A to B, let's go down to D. Remember, we just need to hit every vertex exactly once. We can duplicate edges, but we can't duplicate vertices. So D, let's go down to G. I don't know why I shaded in the edge. Then let's go over to I. Let's go over to H. Okay, so we went A over there up to H. Now look at this. Once we're at H, we can't go back to A because we want to end at A. We can't go to E because if we go to E, then we'd never be able to hit F without duplicating another edge. So the only thing we can do from H is go over to F. Well, and then what can we do? Over to E, up to C, and back to A. So there's one Hamiltonian circuit. This said find two. So first we went from A over to B, so let's instead go A down to H. Here I'm just gonna, I don't know, circle these. A to H, let's go over to E, over to F, over to G, down to I. Remember, we can't duplicate vertices. Up to B, over to D, over to C, and then back to A. So right here we have two Hamiltonian circuits. Now, before going on to this next example, I'd like you to make one observation. I'll call it, before this next example, so I'm going to write it, then I'm going to erase it when I do this example. I would like to write it here, but I don't think I'll have enough room. Remark. If you take, let's take this second one. We went A, H, E, F, E, D, we went like this. Around that rectangle, kind of. Well, you could do that same thing in reverse. Meaning, instead of going A, H, E, F, G, I, B, D, C, back to A, you could do that same thing backwards. A, C, D, B, I, G, F, E, H, A. We're going to consider them the same Hamiltonian circuit, especially for some of the things we're going to be doing after this next example. So I'll just say A, H, E, F, G, I, B, D, C, A, and A, instead of following that, I'm just going to write this backwards. And A, C, D, B, I, G, F, E, H, A. These are going to be considered the same circuit, because one is just the other in reverse. If we're trying to hit all these stations, and doing them in one order and the opposite order, we'll consider the same. We'll also consider it the same if we do it in the same order but start at a different vertex. So we went AH like this around. Well, going from H around following that same path to A and then back to H, we're also going to consider them the same vertex. They're the same circuit. So H, E, F, G, I, B, D, C, A are all the same circuit. This just helps simplify certain things. Like eventually we're going to be looking for all potential Hamiltonian circuits in certain graphs. So if we identify the one going forward and the one going backwards as the same, and identify, like instead of starting here and getting a path, starting here and getting the same run through of the vertices, we're going to consider them all the same. Ooh, that should end at H, because these are going to start and end at the same thing. So these three circuits, we're going to consider all of them the same. Now, not all graphs have Hamiltonian circuits. And right here, I'm just going to give two families of graphs which do not have Hamiltonian circuits. So, this graph. Take two sets of vertices like that. Make them have different numbers of vertices. If they have the same number of vertices, you'd be able to find a Hamiltonian circuit. But if they have a different number of vertices, and you connect everything on one side to everything on the other side, like this, then there will be no Hamiltonian circuit. You can try to find one. We need to hit all 7 of these vertices, start and end at the same one. Well, they have a different number. Let's start here, go over, down, over, 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 and back. But once you get here, you can't get back to the starting point without hitting one of these. And you can try that with any path through here. Like you can go down here, over, up, over, down, over, like that. And again, you're not going to be able to get back to your starting point. So that has... Sorry, I just hiccuped. I hope that doesn't continue. Has no Hamiltonian circuit. And let's look at another. And with that, as I said, you could do any number. You could put 12 edges or 12 nodes on this side, 10 on that side, connect all of them, and you won't be able to find one. But if they do have the same number of vertices on each side, you will be able to find one. Like if they had just 6, you ignore all this. You can just crisscross and go back. Here's another family of graphs with no Hamiltonian circuit. It's going to be an odd by odd grid. This right here, we connect it as a grid. So if this is your, say, street network, you're doing a bus stop at each street corner here, well, you're not going to be able to start and end at the same place without running through the same bus stop once. Let's try. Over, down, over, up. Well, then you hit this, you can't go back. Remember, we're not allowed to duplicate vertices. What if you do something fancier? Well, go over, down, over, 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 up, up. Well, you can't get back there without duplicating a vertex. So that has no Hamiltonian circuit. This one, where it's odd node by odd node, has no Hamiltonian circuit. If it's even by even, or even by odd, it will have a Hamiltonian circuit. I guess I'll draw one of those. Why not? Those have no Hamiltonian circuit. Let's do an even by even. And I'm not going to label these because it's going to be 16 letters, and that's kind of annoying. Well, if you do a 2 by 2, there's a Hamiltonian circuit. You just travel in a square. 4 by 4, more interesting. So a 4 by 4 grid. Well, I didn't fill in the entire grid, but in just filling in part of it, I found a Hamiltonian circuit. There are many Hamiltonian circuits here. So you start and end up here. You can go around like this, back over to this one, down, over, and up. There are many Hamiltonian circuits in an even by even. And similarly, for an even by odd, let's, I have an eraser. I can be lazy with the eraser. If you have even by odd, so here we have a 4 by 3 grid, you can also find a Hamiltonian circuit. This one, it looks like you do have to be a little more clever, because you can't just go all the way around. You'd have to go around and then like zigzag your way back. So around, not zigzag, I mean zigzag following the streets. There's one, and there are others, hitting all vertices. So not all graphs have a Hamiltonian circuit, just like Euler's circuit, not all graphs have one. There is no known condition for whether a general graph has a Hamiltonian circuit. But here, we do have a couple families of graphs which do not have Hamiltonian circuits. Now, we're going to look at a couple applications of Hamiltonian circuits. And to do them, we're going to add certain things to these edges. Before, we added directions to the edges to create a directed graph. Well, here, what we're going to do is add a weight to each edge, a weight, W-E-I-G-H-T. And one application of that is if you're traveling around to a bunch of different cities, and a weight is going to be some sort of a cost in traveling from one to the other. So it could be a direct, like, dollar cost. The next example we're going to look at is going to be a graph where we're trying to visit cities while traveling the fewest number of miles. Example. Consider the graph where the weights represent distances between cities and the nodes represent the cities. So here, these are not accurate numbers because I changed one of this is examples from the textbook. I changed the city up here, Cleveland, to Detroit, so that they started with different letters. And I don't want to have to write CL and CH for Cleveland, Chicago. So these would likely be drawn to scale if Cleveland were up there, but I changed it for convenience. So here we have distances between cities: Detroit, Chicago, St. Louis, Minneapolis. And we have 774 miles, 541, 349, 300, 425, and 562 miles. And our goal is going to be starting and ending in Chicago, visit all cities while minimizing distance traveled, miles traveled. And as I said before, there's no general way to find a Hamiltonian circuit in a given graph. We're going to look at 3 different ways we can go about doing this. Another way we could phrase this question is find a minimum cost Hamiltonian circuit. So I just include this definition here. A minimum cost Hamiltonian circuit is a Hamiltonian circuit with the lowest possible sum of weights on its edges. And there's no general way we can do this, but we'll look at a couple algorithms we could use to find one which may be of minimum cost. This first algorithm will actually give us the minimum cost. The next 2 will not, and we'll talk about them as we get there. But here, for this one, what we're going to do is list out all Hamiltonian circuits and then add up the miles traveled for each one, and then find the one with the smallest miles traveled. Now, how can we list all of them out? Well, we can find all Hamiltonian circuits by using the so-called method of trees. Well, what does that mean? Well, we're going to start and end in Chicago, and we're going to make a tree, well, something that looks like a tree, by picking the choices we can make in each step. So from Chicago, there are 3 different choices we can make. We can go to Minneapolis, so I'll call that M. We can go to St. Louis, I'll call that S. We can go to Detroit, I'll call that D. So from Chicago, we can go to one of those 3 places. Well, what about from Minneapolis? We're trying to visit all cities exactly once. And I didn't write that, that's assumed. From Minneapolis, where can we go? Well, we can't go back to Chicago because we need to visit the other 2 first. So from Minneapolis, you can go Detroit or St. Louis. So Detroit or St. Louis. From St. Louis, you can't go back to Chicago, so you can go to Minneapolis or Detroit. From Detroit, you can't go back to Chicago, so you need to go to either Minneapolis or St. Louis. And now, once we've made our 3rd city, the rest of the path is decided. Because if we visit, in the first example, Chicago, Minneapolis, Detroit, well, then we have to go to St. Louis, and then we have to go back to Chicago. So I'll say back to St. Louis, or over to St. Louis, back to Chicago. If you do Chicago, Minneapolis, St. Louis, well, then you have to go Detroit, back to Chicago. If you go Chicago, St. Louis, Minneapolis, then you need to go to Detroit, back to Chicago. Chicago, St. Louis, Detroit, you need to go Minneapolis, back to Chicago. Chicago, Detroit, Minneapolis, you need to go to St. Louis, back to Chicago. Chicago, Detroit, St. Louis, you need to go to Minneapolis, and then back to Chicago. So right here, we've constructed all possible Hamiltonian circuits. So let's just consolidate them a little. I mean, write them in a more consolidated fashion, I guess I should say. So possible Hamiltonian circuits are the following. So let's just write them going straight down. So CMDSC, CMDSC, CMSDC, CSMDC, CSDMC, CDMSC, and CDSMC. So we used this tree to find a list of all possible Hamiltonian circuits, all possible orders we could go visit all these cities, starting and ending in Chicago. Now it looks like there are 6 we need to consider, but are there actually 6 we need to consider? Let's look at this one and that one. CMDSC, CSDMC. Well, these are going to give us the same total number of miles because one of them is one path and the other is the same path in reverse. And remember, we're considering them the same Hamiltonian circuit. Does that happen again? Well, it actually does. It happens 2 more times. This one and the bottom one. These are also the same. In other words, we don't need to consider both of them. And then that leaves the 3rd one and the 5th one. This is kind of a mess. But the 3rd and the 5th are the same but in reverse. So we have 3 pairs of what we're considering the same Hamiltonian circuit. So we need to consider only only 3 of them. I'm just going to choose the first 3 since they're listed first. CMDSC, CMSDC, and CSMDC. So these are the only 3 paths, circuits we need to consider when trying to determine which one will travel the fewest miles. Now, how do we figure out which one gives the fewest miles? Well, you could just look at the graph and add them all together. I'm going to actually draw out each circuit. I think it's, I mean, you don't have to. And I like it because I think it's more illustrative this way. So we need to consider only these 3. I'm going to write them on these 3 boards. CMDSC, CSMDC, and CMSDC. So what are these going to look like? Well, I'm going to draw out the actual path and then add the miles together. Oh wait, why am I drawing that? I need to add the vertices. Well, I need to put the vertices and then add the edges. We have these vertices. What are they? There's S, M, C, D. So starting and ending Chicago, C to M, M to D, D to S, back to C. That's a terrible edge. Back to C. Let's do the same here. Notice in this circuit you can see, I didn't put any directions here. You could just as easily travel in the opposite direction and get the same number of miles. So we have D, M, S, C, and here we go C, M, S, D, back to C. Notice those 2 circuits are different. And here we have the 3rd different one. So D is up there, M, S, and C. So C to S to M to D. And notice, I guess I could have said this for either the first 2 too. But notice, just like in the tree, when we hit the 3rd city, the rest of the path was determined. Here, once we hit the 3rd city, the rest of the path is determined. We have to go up there and then back there. But here we have the 3 circuits. The 3 possible circuits. Now we just need to figure out which one travels the fewest miles. So let's label all these sides and then add these numbers together. If you want, you can use a calculator to add these numbers together. You know, this is the type of thing I would allow calculators on, because who wants to add all these numbers together? I don't have a calculator near me, so I guess I just have to add them together. M to S, 562, S to C. Well, I guess my cell phone calculator is near me, but that's kind of annoying. I have to open the phone, open the app, deal with the inevitable delay, type the numbers, make sure you type them correctly. So total distance traveled, total distance for the first one, add those together, you get 2,040 miles. I can't read my writing. What's that, an 18? Here, add them together, you get 1877. Yeah, that looks right. And here, total distance traveled is 1985. So that makes this one the one that you travel the fewest miles. So here we wanted to find a minimum cost Hamiltonian circuit. We wanted to visit all cities while traveling the fewest miles. And we did a brute force method. We found all possible paths and then compared the distance traveled. Now, that wasn't too difficult with 4 vertices. But with more than 4 vertices, it becomes much more difficult because of the number of circuits. Here we had just 3 to consider. If you had a graph on 5 vertices instead, there would be 12 to consider. If you had a graph on 6 vertices, there would be 60 you'd have to consider. If you had a graph on 7 vertices, you'd have to consider 360 different Hamiltonian circuits. So this brute force method, it is useful if you have unlimited time, but even the best computers if you had something with like 300 vertices, the best computers can't do that in our lifetime. So the brute force method, while it does give us what we want, is not necessarily the most useful way to find a minimum cost Hamiltonian circuit in practice. So what we're going to do is discuss 2 other algorithms we could use to not necessarily find the minimum cost Hamiltonian circuit, but to find one with close to the minimum cost for a Hamiltonian circuit.